Hello chemists, this is Ms. Placino and you are watching Screencast 8.2 on decay equations. Today we're going to talk about how nuclear decays, more specifically natural transmutations or spontaneous decay, whatever you'd like to call them, are represented as equations. Nuclear reactions are a little different to write from our traditional chemical reactions that we talked about earlier this semester. So we'll review all the basics and give you a chance to practice. All right, when nuclear decay occurs, we have to conserve mass and charge. So if we think back to just balancing regular chemical equations, we had to make sure that we had the same number of atoms of each element on both sides of the equation. In other words, we're always conserving mass. It's not fair to create or destroy matter. When we're doing balancing or writing a nuclear decay equation, we need to balance for mass in a different way. We pay attention to atomic mass of the reactants and atomic mass of the products, and they have to be equal to one another. Additionally, we also have to look at charge. So it's probably easier to look at an example instead of just talking about it more abstractly. We've got to make sure that charge, or you can think about it as the number of protons on both sides of the equation, is also, they're equal to one another. So I know I said it in the previous screencast, but I'll repeat it again. We are looking at changes in the nucleus only. We want to ignore electrons. Don't worry about what they're doing. Don't worry that, as the nucleus changes identity or transmutates from one element to another, is it going to be an ion or an atom? Because what happens to the total number of electrons? Don't stress about it. You're just going to kind of make the whole situation a little bit more confusing. Focus only on the nucleus. More specifically, make sure that mass and charge are conserved. So just to quickly review atomic mass and atomic number and that stuff, atomic mass is the total number of nucleotides. And nucleotides are really just a fancy way of saying protons and neutrons, the only two subatomic particles that we see in the nucleus. The atomic number, it tells us the total number of protons present, and ultimately the number of protons is going to determine the identity of the element. For example, if you've got an atom that has 8 protons in its nucleus, it has to be an atom of oxygen. If it's got 92 protons in its nucleus, it has to be an atom of uranium, so on and so forth. So when we write nuclear decay equations, or nuclear equations in general, we're going to write the element symbol, and then we use atomic mass and atomic number. Sometimes you'll see the atomic number gets omitted. The reason we're able to do that is because, well, if we've got carbon, it's implied that there has to be an atomic number of 6. I'm going to really recommend that you go ahead and take the extra second or two and you include the atomic number, especially as you're just kind of learning how to do this stuff. Because if you don't put it in there, there's a chance you're just not going to balance it correctly. So again, atomic mass, that's our protons plus neutrons. Our atomic number is really just our protons. You can think about that one as charge. We're going to have to make sure that both of those values are balanced as we go and write these equations. Let's start off with something more simple. What I'd like you to do is look at these equations, and I want you to see if you can identify the type of decay that is occurring, or classify the type of nuclear decay that is occurring based on the decay particles that you see. So for example, I'll do the first one with you. I've got uranium. I see that I've got this gamma ray here. So there is an extremely high likelihood that this is just an example of gamma radiation or gamma decay. Go ahead and take care of the other 4 on your own. All right, the second equation is showing us beta decay. We have a beta particle. The third equation, I see it doesn't look like I have really any particle present, but don't forget a helium nucleus is a type of alpha decay. I've got that electron being produced again. That happens in beta decay. And finally, I have a positron being produced, kind of the antimatter of an electron, so that's got to be positron decay. The question sometimes comes up in class, is the second particle always going to be the decay particle? Or like that's the second thing written in the product side, always going to tell you what type of decay is occurring? No, that's purely coincidental at this point. It doesn't really matter whether I put the new nucleus that was formed first, or I put the decay particle first. Either way works. Before we move on to some more complicated examples, we talk about balancing for mass and charge. Let's go ahead and look at this last one. Really what I want to do is make sure that the top number on the reactant side and on the product side is going to be equal. So on the reactant side, I've got an atomic mass of 11. If I check on the reactant side, I see boron with an atomic mass of 11, and I've got a positron with an atomic mass of 0. So that's 11 plus 0 equals 11. I'm balanced. I can also take a look at the charge, our atomic number. I've got a total of 6 on the reactant side. I've got 5 plus 1, so that gives me 6 on the products. That's how I'm going to balance these equations. And we're going to work on applying that with some more practice problems. So I'm going to get over to your workbook and look at those practice problems now. All right, so I want to try just a couple of these. Let's look at the first one. So I've got 5829 copper transmutating into 5828 nickel plus some decay particle. So what I like to do is take a look at my top number, the atomic mass. I guess it's hard to see if I circle it. And I always start there. So I have 58 on the reactant side. I already have 58 on the product side with nickel, so it's safe to say that the mass of particle X is 0. On the reactant side, I have an atomic number of 29. On the product side, I have an atomic number of 28. What plus 28 will give me 29? Hopefully it's pretty clear that that must be something with a charge of plus 1. So I've got no mass and a charge of plus 1. It's going to be a beta plus particle, also known as a positron. So I'd say the decay mode is positron. And that's all we really need to do to solve for the missing part of our equation. Compare your atomic masses on products and reactant side, compare your atomic numbers on products and reactant side, and figure out the symbol. So I'm going to walk through another, let's see which one I want to do. Let's do one that's a little bit more complicated. Let's look at letters. Let's look at letter E. That one's a little bit trickier. So this time I don't know what my reactant is, but I know what my two particles are. So if I look at the atomic mass on the product side, I see 181 plus 4. So that means that X must have a total mass of 185 AMUs. I can do the same thing with the atomic number. I have 77 plus 2. That gives me 79. In order to figure out what the element is, all I really need to do is find atomic number 79. Write that a little neater. On the periodic table. That's telling me the number of protons. Only one element can have 79 protons in its nucleus. Happens to be gold. To classify this, I will call this alpha decay, as an alpha particle is produced. Why don't you take care of B, C, and D on your own? Pause the video, try them out, and we'll get the answers up shortly. All right, you can take a minute and check your work against what we've got on the screen. For letter B, we don't see a change in mass, and we see the atomic number increasing by 1, so this must be a beta decay. Letter C must have been TM168 decaying via electron capture. I know it's electron capture because I see an electron over on my reactant side of the equation. Again, my mass has to equal 168 because that's what I've got on the product side. And I guess I need an atomic number that's equal to 68. So 69 minus 1 gives me 68. And finally, with letter D, we have positron decay again. And our other decay, I guess our new nucleus produced, I should say, is scandium SC45. All right. So that's it as far as trying to solve for X. The most complicated ones that I can give you are where you've got to write the full equation. So for these last type, you're going to try to write out the balanced decay equation for each radioisotope. And if you look, you don't really have much information at all. We've got thorium-232. So I'm just going to start by writing that information down. I can look at a periodic table or my reference table and see that thorium, that's kind of tough to read, is element 90. Then I'm kind of on my own. So I could probably figure out, based on the different decay modes and the ratio of protons to neutrons, what the most likely decay mode is. New York State is not interested in you really understanding why nuclear decay occurs. They're very interested in your ability to read a table. So I'm going to pull up your reference table and show you a gigantic cheat sheet that you get for this unit. Here we go. Table N. Table N is packed full of information. They've given you selected radioisotopes, half-life, which is something we'll be talking about more in a future lesson. Right now, what we're most interested in is decay mode. So we just were looking at thorium-232. The way I'd use this table is I'd find my radioisotope of interest, thorium-232, and I'm interested in this. So I see an alpha particle, so this is telling me that thorium-232 undergoes alpha decay. And really, hopefully that shouldn't be a surprise. Thorium is a massive nucleus, and very large nuclei tend to undergo alpha decay. Back to the practice problems. So I know I'm going to undergo alpha decay, and I'm going to be specific. I'm going to write 4,2 He. If you want to represent that as just an alpha particle, that's fine as well. I'm going to do something like this. But I would encourage you to write down the 4 and the 2. I know that my nuclear equations have to be balanced for mass and for charge. I have a total of 232 AMUs on my reactant side. I have 4 on my products. Doing hopefully some simple subtraction, I come up with 228 as my mass. I'll repeat the same idea with the number of protons or atomic number. I must have 88. And then going back and looking at a reference table of some sort, or a periodic table. This one's going to be, 88 gives us Ra, radium. We'll go back to that. That's all there is to it. Use table N to figure out what sort of decay mode your radioisotope in question will undergo, and then balance it, making sure that you got the same atomic number and atomic mass on both sides of the equation. Go ahead and try letters B and C on your own, and I'll get the answers up here in just a moment. Take a second to check your work against what we've got here on the screen. So first we have the decay of phosphorus 32. If you look at table N, you'll see that it undergoes beta decay. It's because we have an unfavorable ratio of protons to neutrons. That's the whole reason any of these decays occur. But more specifically, there are too many neutrons present. So a neutron turns into a proton, and I end up with sulfur with a mass of 32. And we can double check 0 plus 32 equals 32. Great. 16 plus minus 1 equals 15. Perfect. That works out. For iron 53, it's the same procedure. Check table N. You'll find that it undergoes beta plus decay, also known as positron decay. So I'm going to write my positron particle symbol, 0 over plus 1, and sometimes you'll see it with an electron or a B plus. Surprise me, I don't care. Balance for mass and for charge. I've got 0 plus 53 equals 53. Perfect. I've got 25 plus 1 equals 26. That's balanced as well, so I know that my equation is correctly written. One thing to kind of take note of, because we're going to build on this more in the next lesson, is with all of our natural transmutations or spontaneous decays, we always seem to be starting with just one reactant and then forming multiple products, with the exception of electron capture. But alpha, beta, gamma, positron, they all take on this format. One reactant turns into multiple products. We're going to, like I said, kind of build on this in future lessons as we talk about other types of nuclear reactions that can take place. All right, that wraps it up for today. Thank you for tuning in, and I hope you found this helpful.